Dear colleagues, we present a report on the topic Test Platform for Simulation in Hardware of Unmanned Aerial Vehicle on Board Computer. My name is Arsen Petrosyan. I am a graduate student of the Department of Software Engineering of Zhytomyr Polytechnic. Designing and developing software for controlling UAV orientation in space takes a long time, including time for debugging, testing, and flight tests. Using classical methods of debugging and testing flight controller firmware is problematic. Step-by-step debugging, generating messages to the console, using a logic analyzer, etc. Mistakes made in the development of UAV software can lead to emergencies or other unforeseen failures during operation. In this regard, the task of checking the reliability of the UAV's onboard computer software arises, which will simplify the maintenance, modernization, and optimization of the software. The purpose of the work is to develop a test platform for UAV using 3D virtual environment. To achieve the goal in the work, the following tasks must be solved: analyze software testing approaches, development of the test platform structure, development of sensor and actuator simulator. According to the degree of code isolation, there are four levels of testing: unit testing, integration testing, system testing, and acceptance testing. However, we have software being developed not for a computer, but for an embedded system. An embedded system is a specialized computer system or computing device designed to perform a limited number of functions, often in real time. Embedded systems often need to work in interaction with the environment, using sensors to obtain input data, temperature, pressure, etc. And UAVs are no exception. The figure shows a simplified architecture of the UAV and its content. It can be seen that many different sensors are used as part of the UAV. Firmware is a software embedded in a hardware device, such as a calculator, GPS navigator, UAV flight controller, etc. The difficulty in testing UAV firmware is that the system is closed loop. You can see from the figure that it is not possible to stop the firmware from running, as the system will stop functioning. Obviously, a UAV is a complex hardware and software system, which creates difficulties in generating a complete set of sensor signals and the impossibility of creating emergency situations on a real UAV. To solve these problems, special software and hardware are used in the development, debugging, and testing of UAV firmware. One variant of testing UAV flight controller algorithms is to use a mechanical test platform with 3 degrees of freedom, rotation. It is also possible to move the platform with restrictions. The disadvantages of this option include the bulky platform. One of the effective methods of testing embedded systems is simulation modeling. Simulation modeling is a research method that uses models that describe real-world processes. Using such models, it is possible to test the real system without exposing it to danger. The simulation is performed using a virtual 3D environment. However, it should be borne in mind that 3D UAV simulators can be divided into two groups by functionality: simulators for training UAV operators, and simulators for developers to test and debug UAV flight controller algorithms. This slide shows screenshots of two of the most popular UAV flight training simulators. Most often, these simulators have good graphics and have the ability to connect a remote control UAV. This slide shows screenshots of simulators for UAV developers. Also, this first simulator is intended for operators, but due to the possibility of creating plugins for it, it can be referred to Universal Simulator. The second is a popular open source simulator for robotics. The firmware test in UAV simulation can be performed in three places: on a host computer, using code compilation for the source platform; in an emulator on a host computer, such as Camo; or on a real flight controller, using cross-compilation of code for the target device. The first two variants are used when performing SEAL, software in the loop simulation. The latter variant can be used in HIL, means hardware in the loop, or SIG, means simulation in hardware simulation. This slide shows the structure of SEAL simulation. This slide shows the structure of hill simulation. As we can see, the structures are similar, only in the first case firmware flashing is performed in the software emulator, and in the second case in real device. The main disadvantage of such variants of test system, like firmware modifications are required, use of non-proprietary interfaces, and bulky system. Our work recommends the use of SIG simulation. In the first proposed SIG simulator architecture using sensor and actuator simulator, this approach allows to eliminate the above-mentioned disadvantages. The main advantage of our approach is the ability to organize testing of any flight controller without having its source code. The sensor and actuator simulator performs the functions of real devices. The sensor and actuator simulator is configured similarly to its prototype, and the data registers are filled with information coming from a personal computer with a 3D environment. The software of the sensor and actuator simulator is implemented in the C++ programming language. For sensors with an I2C interface, the basis is an abstract class shown in the screen. To configure the sensor and actuator simulator, we developed a simple utility in the C++ programming language using the Qt framework. For each channel, the sensor model, interface, and variable address part, as well as the noise parameters are configured. Thanks everyone for attention.